the Orient, South America, Central America. I've done quite a bit of flying. I've flown all my life.
I travel probably more than 75,000 miles a year by air.
I love flying. I love the idea of displacement.
We think of a grand piano as being a heavy object, too heavy to fly, but a 747 has about 5 times the wing loading of a grand piano.
There is something of the nomad in all of us. And we have a love affair with flight. Economics aside, it means that no two people on Earth need be more than a day or two apart.
Here you go. Have a nice flight. Thank you.
When men came to Kitty Hawk in the early morning of the century, they brought little knowledge, but great vision. Montgomery, Lilienthal, before them had shaped the wing, but they opened a new dimension to flight. Flight was to be a leap into the sky. A powered leap. Flight is a day's work, and yet flight is beautiful, an art form of our time.
I think it's self-evident that there are many areas in the world that need a really useful airplane, and this requirement hasn't yet been satisfied, and this airplane is my contribution to that. I believe that many parts of the world would like to have the social and economic benefit of building a very simple airplane and then subsequently putting it into operation. And then this airplane, it will carry pigs to market, granny to hospital, crop spraying, a very versatile airplane, and I believe this makes it the most suitable and wanted airplane in the world today.
The most wanted plane today? It's not quite that simple. The economics of flight is, unfortunately, far more complex. For flight must pay its way in a competitive world. Flight is employment. It is big business. The competition for business is intense. The problems are many. The pressure's real. We are at the crossroads. Dwindling finances for new planes, spiraling costs, uncertain fare structures, crowded airports, noise, air pollution, and the problem of safety in the air. The world has learned to fly in American aircraft. Our flying machines, where will they take us in the future?
The United States has always been able to stay ahead by using technology faster than any other country. Most of the civilized countries know this technology, but they are much slower in getting it from the lab into the airplane.
But this is changing. And failure to maintain technical superiority now can cost us nearly 1/3 of our historic share of the $50 billion market in 10 years. Research is part of the answer. The sweeping arc of turbine blade design, modern art.
We come to the leading edge, and its radius is well within a tolerance and a beautiful profile.
Aircraft markets of the future will go to the safe, energy-efficient aircraft. Our research extends in this direction. We are forming airframe structures of strong, light composite materials. Mixtures of epoxy with fibers of boron, graphite, or aluminum. We look into the problem of wear and friction in large turbofan engines and quiet, clean turbofans for general aviation. Propulsion systems of the future concern us. Hydrocarbon fuels from oil shale or coal. Exotic fuels, possibly hydrogen.
You know, I graduated from college 23 years ago as an aeronautical engineer, and we were doing much of the work in the wind tunnels and in theory in those days with the kind of research that winds up in an airplane like this 23 years later. And I think what people don't realize is how long it takes to develop an airplane and how much research goes into technology that winds up as a practical application in all the different kind of airplanes that are used in the world today.
The dreams of the Wright brothers were tempered by reality. To understand flight, they first used basic models and gliders.
The model is much less cost to build and to fly. The operation of the model is much simpler. You don't have the man on board to risk his life, and we get to see what the airplane will do in a model before we take it up on the full-size vehicle.
Aerodynamic research begins with models, exact miniatures of craft that are or will be. The model makers, craftsmen with the skills of an artist. Models are the bridge between theory and reality. Our research takes us into every area, every conceivable problem of aeronautics. The ways of reducing drag, smoothing the flow of air over wings and tail. Maneuverability in the hypersonic planes of the future. The ultimate test of theory here is the wind tunnel.
95 miles, point 972.
Point 972.
I'm going to tab point 167B right now.
Okay, we got it. 979.
Wing flutter can tear an aircraft apart.
972. 959.
In the transonic dynamic tunnel, a model of NASA's supercritical wing comes to the threshold of serious flutter.
Okay, G, we're getting really close to flutter now.
2503. 503.
Okay, here we go. Okay, hit it.
179.
Success here can pay off through increased range, energy efficiency, and greater maneuverability. The ability to maneuver was a factor even in the beginning. 3 years later, the Wrights were to fly with the gasoline engine.
I think what we'll do is to put a fillet right in here that will smooth the flow out a little bit.
Richard Whitcomb, leading NASA scientist.
Probably should be reduced so that the airflow will better work on it. The winglet takes advantage of the cross flow at the wingtip. The flow at the tip is moving inward.
Right.
And therefore it pushes on the winglet, and there's a side force on the winglet. That is a force in this direction.
Sure.
And
There are possible fuel savings.
has a vector, or it tends to tilt.
In the California sun, a 20-year-old airplane keeps an early appointment. The research focus is on short-haul aircraft and on vertical flight to a takeoff or a landing. Our future may see short-haul airliners with a tilt rotor, enabling passengers to board the airplane in mid-city, fly to another city, and make a vertical descent to a landing.
Looks like we completed that run, Steve. Our touchdown speed was good. Our vertical speed was down to about 50, and we were within the nominal touchdown zone. We're about 10 feet to the left of the center line.
Okay, glad that's behind us. We're getting a printout now of the data on the strip recorder, so I guess we can change over to that 61 helicopter.
Roger, sounds good.
Let me know when you're ready.
Some flight experience is found in a simulator.
Okay, we're just about ready. Okay, send us the static voltages now, Steve.
Okay, true ground and alpha.
Roger, look good.
Helicopter instrument landings.
Good. Your control is...
Improved all-weather landing procedures.
Roger, we'll switch to Carmel 3 and arrival time of 1732.
Ames approach control, American 301.
We study pilot responses.
American 301 is Ames Stollport. You clear for the Apollo approach.
Okay, we're understanding.
The number of voice reports a pilot must make affects safety.
American 301, say speed, please.
American 301 is indicating 100 knots.
American 301, can you reduce 10 knots, please?
In this aircraft, we have two cockpits, the normal flight station and one within the fuselage behind this hood. Aviation has long recognized the need for an automatic all-weather control system, one less susceptible to human error. NASA, with the Federal Aviation Administration, has flown this 737 through hundreds of hands-off, automated, microwave-controlled landings.
Joel, stand by to put me in auto. Okay, couple it now. Auto, 3D.
Auto, horizontal path.
That looks good.
Could we have video and DAS on?
Roger, we're 20 seconds to descent now at 4AC05. Gear down.
Okay, this will be MLS 1B2.
25.
The SKC configuration 4A. And pilots be on the lookout for any different behavior when we acquire EL2 signal.
Roger. Okay.
This system is well on the way to setting the world's standards in this area. If we look to the future of aviation, with its requirement for error-free pilots, crews, air controllers, we can only conclude that human factors is the least advanced of our technologies. We study what instruments the pilot actually sees, what his vision scan includes in an instrument landing. We look into the complex problem of pilot disorientation. Does the pilot see what he thinks he sees? How soon can the co-pilot take over control of the aircraft if disorientation occurs? The spin, the fighter pilot's deadly companion. For 75 years, the problem of stall spin has threatened flight.
How do you know that the accidents that took place were due to stall spin?
That information came from a special study made by the Air Force because of the concern over this problem, and of a joint program which we are engaged in with the Air Force to see if we can eliminate that problem.
He was floating along when a wind with an upturn trend struck him.
Wilbur Wright on the death of Otto Lilienthal.
But the gust suddenly dying out. The speed increased rapidly. With a smaller angle of incidence, the center of pressure moved farther and farther back and turned the surfaces over more and more till it struck the ground with frightful velocity.
In general aviation, the objective is to provide design data for an efficient light aircraft which will not enter into an unintentional stall or spin. About 80% of the air transportation accidents on and around airports are the result of human error. One of a series of crash-worthiness tests to determine what happens to the structure of an aircraft upon impact. The private pilot, one of almost 700,000 in the United States. General aviation aircraft outnumber airliners by a ratio of 100 to 1.
That's a 340, clear for touch and go.
Safety is a serious concern. Although the number of accidents continues to decline, there is still room for improvement. As an example, we're concerned with mid-air collisions, from 25 to 40 each year. General aviation pilots need a simple, effective crash avoidance warning system. The supercritical wing, the cross-section of the shape of the future, flying on the Air Force's YC-15. For For the first time, a helicopter has been designed from the start as a research vehicle. With this craft, we can measure and define the forces which control helicopter flight. The Blackbird investigates supersonic cruise problems at high altitude. It operates at speeds which turn wing and tail leading edges red hot. We call it fly-by-wire. The conventional controls have been removed. The pilot flies the aircraft through a computer which in turn works the controls. Fly-by-wire. Flight verification for the Space Shuttle's control systems.
Altimeter.
A computer gives pilots airport, flight, and services information.
Fuel.
Fuel available during daylight hours only.
The pilot is aircraft. And NASA's overriding concern for safety in the air. Our flying machines. Even in the beginning, we knew this to be a love affair.
For the past 70 years, aeronautical developments have emphasized greater increases in performance, carrying more passengers, more cargo, higher, farther, faster. These developments, by and large, have met the public and economic needs of the nations of the world. I think we're at the end of a phase now in which we'll have to examine more closely the goals of aeronautical research. Providing more performance may not be the answer. We'll have to look at meeting social and economic needs, which may or may not require higher performance, greater speeds. Emphasis on reduced pollution, carrying goods and people more cheaply may be the answer.
This was a living community. The people had to go. The effect of aircraft noise on our lives is a serious problem. Many cities place a curfew on their airport, restricting the nighttime hours of operation. To avoid the cities, pilots must fly complex departure and arrival routes at reduced power. The Concorde is here. But noise from our jets was here before it came. It is a problem which won't go away. Research in the 1960s led to new engine designs and acoustic suppression. The jet engines of today are quieter than those of yesterday. We are also concerned with the noise made by the passage of air over aircraft surfaces, aerodynamic noise. This is a part of the total noise we hear. NASA's quiet engine, a new design from core out. This engine demonstrates the noise reduction technology for jet engines of the future. .97 decibels, a reduction of 20 decibels. Aircraft operational by the 1990s will use this technology. Space Shuttle's Enterprise, astride a Boeing 747, for a series of systems and aerodynamic flight tests over the California desert.
Okay, hold on.
Okay, Larry, we're ready for airspeed and altitude check on number 8. That looks like 101 over here. Is that about what you guys want? Okay.
Space Shuttle, a compatible marriage of aeronautics and space technology. Charles Lindbergh's Spirit of St. Louis and the Wright brothers' first powered flyer. 24 years separates them, and just a few scant feet brings them together. It is a wonder that all this has happened before our eyes in this century. The future, too, will be here for our amazement. Kitty Hawk and Space Shuttle's Enterprise are very close indeed. We have a love affair with flight.